Hey guys. So I want to do a review of Mrs. Hecker's first lesson here from Chapter 1, Section 1. So you can see on the screen here that we have three different boxes. The three things she talked about is one, expressing um, the multiples of problems such as this, like 4 times 4, 5 times 5 times 5 times 5. And C as well, you can see like how do we write those as an exponent. So we're going to go through that. We're going to look at how to expand and solve exponents, and then we're also going to look at perfect squares. So that's our goal. So if you want to just quickly see exactly how to do these three, just watch real quick. Pretty simple. So let's take a look at the first one here. Let's look at how do we actually express these numbers as an exponent. Well, it's real simple. So let me select my tool here and let's take a look. So what we want to look at is how many numbers do we see? So we have a 4 times a 4. So we see two numbers. Now what you're going to do is you're going to use the numbers that you see here as your base. Okay, so your base, you're just going to take the number here, you're going to extract it out, and you're actually going to put that number there. So you can put 4. Well, now how many 4s do you see? That's your exponent. So your exponent goes right here. That is your little number. So the way we would read this is 4 squared, because or you could say 4 to the power of 2, or 4 to the second power. There's a few different ways that you could actually say it. Whatever you're most comfortable with, all three of them are correct. So let's take a look at the next one now. Now we have 5 times 5 times 5 times 5. So again, your base is going to be the number that is given to you that you see right there. So we're going to just immediately write that number down. We have a 5. And then we're just going to count up how many 5s we have, and we're going to use that as our exponent. So we have 1, 2, 3, 4. So it's going to be 5 to the fourth power. So we get that in there. There we go. So 5 to the fourth power. And then the final one here, we're using our 13s. If we want to write this one, it's the same thing as what we just did with both of these. And this one's going to be 13 times 13 times 13 times 13 times 13 times 13. That's a big one. So again, we have our base, which is going to be 13. Oh, sorry. Oh my gosh, that was terrible. Let me erase that. Let's try that again. Okay, so we have 13. Sorry, it's hard to use these tools sometimes. So 13, now how many 13s do we have? So we have 1, 2, 3, 4, 5, 6. So it's going to be 13 to the power of 6. Now sometimes, that's hard to see there. So sometimes she's actually going to ask you to solve these. So it's not just writing it as an exponent. You actually have to say that this equals what? What is 4 to the second power? Well, it's the same thing as 4 times 4. So 4 to the second power is 16, right? Trying to get that in there. Good. Okay, that's a 16. The next one here is 5 times 5 times 5 times 5. Well, it's going to be 5 times 5, which is 25, times another 5 is 125. And then if you take that, then we got a bigger number. So you might want to pull out a calculator just to make sure that you're correct. And you just do 125 times 5, which is going to give you 625. Gosh, I wish these sixes would stop showing up because they're hard to do on here. Oh, there we go. 6, 2, and 5. Try not to bleed into that bottom problem down there. So 625. And then you could go ahead and you can do this one as well. 13 to the sixth power. So again, you're going to take your calculator. Now this is a much bigger number. So you're going to do 13 times 13 times another 13. That's 3 of them. Times another 13. That's 4. Times another 13. Times one more. So now we got a big number. I'm not even going to put it on there because it's 4,826,809. Yeah, I'm not going to be writing that one, so that's okay. Okay, so that's how you take it when you have it in expanded form and you want to express it as an exponent and then solve. That's what you do. Okay, now the next part here, expand and solve each exponent. So I'm going to write in an exponent here. And let's go with let's just try this one. 11, start easy, 11 squared. So if we're given this one, 11 squared, how do we actually write that in expanded form? Well, it's easy. Here's your base number, right? And then you just look at your exponent here, and it tells you how many of the base you are going to multiply. So if you have an 11, how many are we going to multiply? We're going to multiply that twice. But we're not going to do 11 times 2. Biggest mistake going. So what we want to do is 11 times, and that dot is actually another way of writing a time sign. 11 times 11. Okay? That's all you have to do. Let's try another one. I'm going to change colors here. And we're going to go with a 15. Oof, boy, I'm having a really hard time with this writing tool here. Try and hook that down. That is a 15. Hold on, we can do better than that. Oh my goodness, we can do better. Okay, let's try this again. So, and I don't like that color. It matches up too much with the others. Let's try this. 15. There we go. I'm going to try 15 to the third power. Should have had my mouse with me. It would have been easier. All right, so 15 to the third power is equal to, again, 15, boom, times 15, okay, times 15. Because 15 is our base, and we know that the exponent is 3, and it's telling us to multiply that base number 3 times. So you want to write it as 15 times 15 times 15, okay? All right, and then the last one here, let's go with some green. Let's just do a simple number here. Let's go with a 7, and we're going to do it to the, I guess we'll go to the 5th power. So 7 to the 5th power. Okay, again, just like before, you look at that larger looking number is your base number. So we're going to do 7, and how many times are we going to multiply the 7? Well, that's the exponent. 7 times 7 times 7 times 7 times 7. Perfect. There we go. And then our last one here, do we have perfect squares? So as Mrs. Hecker had said in class, like a perfect square is when you can take two of the same number, multiply them together, and if you tried to form them using little chips, that would actually form a perfect square. So let's take this first one for example. We have 100. So 100, you have to think to yourself, what number can I multiply by itself to get that number? So is it a perfect square? And is there something that we can multiply twice to get 100? Well, yeah, absolutely there is. That's the number 10. So we're going to say 10 times 10, oh, we're getting there, would make a perfect square because it equals 100. So how do we prove that? Well, you could say that if we had 10 on this side of a square, we had 10 boxes there, we started going this way too, and we had 10 up here. Yeah, this is how it works, because you have one side that's the length of 10, you have another side that's a length of 10, and that means that if we went this way, that would be 10, and this would be 10. That's how it works. So anytime you multiply a number by itself, you have a perfect square. So another way of expressing this would be 10, these are always to the power of 2. So 10 squared. Whoa, not sure what happened there. We could do it better too than that. Do not know what happened. So 10 to the power of 2. Perfect. And then the second to last one here, we have the number 25. Is that a perfect square? Well, yes, it is. Let me change my color here. So because we have to think to ourselves, what number can we multiply to get 25? And can we multiply it by itself? And yes, we know that that number is 5. So we can do 5 times 5. Boom. 5 times 5 is 25, so yes, it makes a perfect square. You could also write it as 5 squared. Okay, they all equal the same thing. They're called perfect squares. What about 30? Is 30 a perfect square? Can we multiply anything to get 30? Let's go. Let's try. Okay, if we're at 5 times 5 is 25, well, then the next number up is 6. 6 times 6, well, that's 36. So that goes over 30. It falls right in between those two. But there's nothing that you can multiply to get 30. So this one, we are just going to write as, we could just say NA, not applicable, or actually, let's just put no. It is not a perfect square. Because again, you don't have two numbers that you can actually multiply. So this is lesson 1.1, a quick glimpse of it. If you have questions, again, don't be afraid to email me, ask during class, ask Mrs. Hecker. We're there to help. All right, guys. I'll see you later. Bye.